this. And don't forget, we're shooting for a quiz next Friday for green, and then the following Monday for blue. And that's pretty much going to cover a big chunk of Chapter 2. If you want to be preparing for it right now, which you should be, just be looking at those exams and looking at the questions about kinematics. All right. Some of them might look a little foreign to you. You can look ahead into the notes if you like, and then go look at the solutions online too. That's really the way you do well in this class, is practice, practice, practice. So I'm going to pull up some of the exams. I'm going to look at some of the older ones, like before 16, and that way they'll just be fresh, different things that we're doing. So let's look at the dimensional analysis. We'll look at this number 3. This is fall 15 for exam 1. And we had a similar question, I think, on the quiz today, or if y'all took the quiz. By the way, Monday's quiz will be different, FYI. So on these dimensional analysis, you want to put the units into each variable. This first one has something a little bit different, where it has the v squared equals v0 squared plus 2ax. Often this v0, what that denotes is an initial condition. And so the 0 is at t equals 0. We just write it shorthand. So at the time, at 0 time, and often we'll say that it's v naught, like all for naught, that kind of thing. It means nothing. And so that's the symbol for our initial condition. And so for this one, I would have meters per second squared equals, this one is also going to be meters per second. And then both of them are squared because it's v squared. And then the a is meters per second squared meters. And so that is a correct equation. This second one, I think this one's correct too. 1/2 mv squared. So the halves, all the constants, just don't count at all. They don't have any units as far as we're concerned. I can also look at this equation, and I'd have mv squared plus xma plus mx squared over equals mx squared over t. I can look at that and make it a little simpler by getting rid of all the m's. By the way, let me just warn you to be careful when you're doing these, because you have some variables that use the same letter as the units. So when I use m as a variable, that means mass. But when I use m as a unit, that means meters. So just be careful, be aware. I think m is the only one that's used in both. So just be aware of that. V squared is meters squared per second squared plus meters per second squared. So far, correct so far? Yeah, so far we're okay. And then I have equals to meters squared, that's x squared, divided by second. And so now I run into a problem, right? That this is not a dimensionally correct equation. And then the third one is v equals x over t. And v equals x over t, meters per second on one side and meters per second on the other side. Now by the time you get to the exam, you'll know that that's one of our basic kinematic equations for velocity as position over time. So you'll recognize that as an equation. This one is not terribly difficult. Let's see if there's another one that might be a little trickier. I'm going to go back to the fall 14 exam and see if there's one where we have, yeah, let's try this one. I want to look particularly, this is fall 14, exam 1. I'm just going to look at this second one right here, the MAV over X. Whenever we have variables in the denominator, it just gets a little more complicated. And so I'm going to do that one. It's going to be MAV over X is equal to MV cubed over X squared. So I want to know, is that dimensionally correct? Oh, actually, you know, this one isn't too terribly difficult because I can get rid of some variables right off. Oh gosh, I see 3 that I can get rid of. Do you see them? MV and A, right? Or MV and not A, X. Yeah, M, I can get rid of one of these V's and this becomes a 2. And I can get rid of this X right here and this just becomes X, not X squared. And so A is equal to V over X. I already know right away that that's not correct, right? Because we defined acceleration in chapter 2 as velocity over time. So not right, but we can just confirm that by looking at the units. Meters per second squared equals meters per second. And then I need to be careful when I write the X. Sometimes students will write it up here as meters, but that's not correct because the meters is actually in the denominator. And so that cancels out with that. A meter per second squared on one side and seconds on the other side. Let me just make up an example right here. If I have, say, oh, I'm just going to do a single expression, not an equation. So I have xv over a. And I want to know what the units of that are. This is more difficult because acceleration has a numerator and a denominator, right? It's meters per second squared. And so when I have 1 over a, that's going to be equivalent to seconds squared over meters. So when I write this, this is going to be meters per second. I like to just spread everything out. Okay, just break apart that fraction and keep what I have in the numerator in the numerator, and what I have in the denominator, either I'll keep it in the denominator or I'll flip it like I'm about to do for acceleration. It's going to be seconds squared over meters. And then this mass cancels, or excuse me, that length cancels. This time cancels, and I'm just left with meter seconds. Okay? 2 or 3 questions. Those of you who took the quiz today. All of you. Okay. How'd y'all do on it?
Did you post it?
Huh? I haven't posted it yet, but how did you feel like you did? Okay. Well, you know what? We're going to have lots of quizzes. So if you didn't do well, don't sweat it.
Just nervous about my clicker not submitted. So if it lets it check mark my each one, then it's submitted. Okay.
Yeah. I rarely have issues with clickers. So if you have some issue, you come see me. If you feel like it's not right, I have your paper version so we can look at it. But you know, in general, the clicker is the final answer, because I know y'all don't do this because y'all are honest and upright and have great integrity. But sometimes students will put one answer on the paper and one answer on the clicker, and then it's like they're playing the game. So that's why we do that. Why we say this is your final answer. But that's not y'all. I know that. In fact, that's hardly anybody in the class. It's just one person in the last 15 years. Okay. Approximations? Yeah, we'll just do 1 or 2, okay? Because I think that, let's just do number 6. Because number 6 is not only an approximation. Again, this is fall 14. Number 6, exam 1. Number 6 is not only an approximation, but it's also a unit conversion. So a pencil is about like this, and a pencil in centimeters, which is the most useful unit to measure a pencil in, is about, well, it's about 15 or 20 centimeters long. My pen's a little shorter than a pencil, but a pencil is usually about 20 centimeters long. But notice here that I'm not asking for it in meters. I'm asking for it in meters. And so you have to convert that centimeters, 20 centimeters, into meters. And to do so, you do your conversion factor. You should know your metric prefixes. You should know nano, micro, milli, centi, kilo, mega, and giga. Okay? Or as my graduate advisor called it, he always said it was giga. Like you say gigahertz, right? Y'all say gigahertz? He would always say gigahertz. And his reason was that you don't say gigantic, do you? You say gigantic, right? When you say that something's gigantic. And so you should say a similar thing for gigahertz, or using the prefix giga. Anyway, you can use giga if you want. So 20 centimeters, there are 100 centimeters in 1 meter. And so that's equal to 0.2 meters. So that was the answer to that approximation. Sometimes, too, in those approximations, it's not just an approximation, but it's converting, and sometimes it's like an area. You might have seen a question like that, where I asked for the area in millimeters squared, or something along those lines. And millimeters squared are kind of hard to estimate, but it's easy to estimate centimeters, or it's easier because you have a reference about the width of your pinky, and then you just convert that into millimeters. You know how to do that? With powers? Let me show you right quick. Let's say that I had 20 square centimeters, and I wanted to convert that into millimeters. Well, I would have to do my conversion. I'm going to take it in 2 steps. Go from centimeters to meters, and then meters to millimeters. It's a little simpler in that way. I have 100 centimeters in a meter, and I have 1,000 millimeters in a meter. In both of these cases, these unit conversions have to be squared. And so I'd have 20 divided by 100 squared times 1,000 squared. And then that would be my answer, whatever that is. What's that? 10 to the 4th, 10 to the 6th, 2,000, I think. I don't know. Anyway, that would be my answer in square millimeters. You're going to have to do power conversions like that, where you convert one unit to another with powers, squares, cubes, either squares or cubes. If you don't know how to do that, come see me. I can help you. Like if you're struggling with those things, we really need to take care of that business right now. And we can. I know if it's overwhelming, we can take care of that right now. But just come see me. We'll spend some time practicing in my office. All right. Can we do some kinematics? Okay. We want to do one like the graph that you have. It was sort of like this one, right? But it was a curved graph, right? Yeah, okay. Yeah, those are a little more complicated. They're on every test, though. So, oh, this is a good one. They're on every test. So I always have graphing questions. And there's going to be one like this where it's a non-linear graph. Then there will be another one where it's a linear graph. And then there'll be qualitative graphs, too, where you have to talk about what is the slope, is it increasing or decreasing, like we did in class today. Everybody's blue here, right? Yeah, look at your blue shirts. Yeah, or 2 of you have blue shirts. So consider this velocity versus time graph. First of all, a couple of things you need to know. The slope of a v versus t graph is equal to the acceleration, and the area of a v versus t is equal to the distance traveled. And so here I want to know the acceleration at t equal 4 seconds. Usually when I give you these, I'll give you a section of the graph that is fairly linear. And so you'll be able to figure out you'll be able to draw a straight line at that point. So at t equal 4 seconds, I need to draw a line that is tangent to that point. And so it's going to look something like this. All right. Let's see, what is the answer? Okay. Then if I want to know the acceleration at t equal 4 seconds, then I just take the slope of that line. And so I'll draw down here like this. That's my rise. I go from 0 to 10, or rather from 10 to 0, so it'd be 0 minus 10 is equal to negative 10. And then my run goes from 3 to 5, and so 5 minus 3 is equal to 2. Don't count the squares, okay, because I know that if I were to give this question on the test, I would get some students that would count the squares. They would say 5 squares is my rise, 2 squares is my run, 5 divided by 2 is minus 2.5. Actually, I don't see that here, but they would. No, they would probably put D. They would probably put D. for this answer if you're just counting the squares. Okay, so if I want to know the velocity at this point, or the acceleration, excuse me, which is the slope of that, is going to be minus 10 divided by 2, which is negative 5 meters per second squared. I can check my units because this is meters per second and this is seconds. And meters per second divided by seconds, which is the same as saying this is equal to meters per second squared. So that's correct. The next part of this question, usually on these graphing questions, I give you multiple parts because I like to use the figure, for multiple questions. The next part is asked, what is the total distance traveled between 2 and 5 seconds? If the slope of the graph is the acceleration, the area of the graph is the distance traveled. You had calculus yet? Some maybe in high school a little bit, or maybe you're in calculus now. When I talk about the slope is really just a key word for the derivative, dv dt. If you've seen that before, that's what that is. The derivative is really just the slope of a graph. And so the acceleration is defined as dv dt. You don't need to write that down. You don't need to know that, but that's what the derivative means. It is the slope. The area of a graph, on the other hand, in calculus speak, is equal to the integral. And so the integral is really just calculating the area underneath a function. And in this case, it's going to be the integral of v dt. Notice this is the rise, or not the rise, I'm sorry, this is the y-axis, this is the x-axis. You can think of it in that way. And when I'm doing that, I'm taking the product of those two, v and t, and I get the area underneath that curve. So calculus is really just all about calculating the slope and the area. And that's, that's the most important part of that in terms of kinematics. Now, I was looking here for the distance traveled between 2 and 5 seconds. I'm going to erase some of this stuff on the graph. I'm looking at 2 to 5 seconds. I'm looking to go from here to here. And what I need to do is I need to find the area of this graph. The best way to do this is just to look at each individual square and ask how much distance does that square represent. So if I look at this square right here, it represents how many meters? What is the area of that square? 2, right, because I have a 2 right here and a 1 right here, so the area of that rectangle is equal to 2. So each square represents 2 meters. And then I count squares. 1, 2, 3, 4, 5, 6, 7, 8. I would make this 9. I would sort of join up these two. That's 10. And then we'll just say that's 11. I don't know, 12. We'll just say it's 12. We're really just sort of estimating it. I know it's not quite 12. It's somewhere between 11 and 12 squares. And if each one is 2, then I know that my distance is going to be somewhere 22 to 24 meters, somewhere around that. Let's go down and look at the answers. Oh, look at there. 23 has to be my answer. All those others are just, they're not reasonable answers. You will have a question like that. You're going to have a whole series of questions where you have to find the slope or the area of a graph like that. Y'all could do that? If I gave it to you today, could you do it? Like right now? You want to do a quiz right now? Okay, you will be able to, though, because you know how to calculate area. You know how to calculate slope. It's really just applying it in these different situations. And there are a lot of different situations, so, it's not easy. But with practice, it will be easier. All right. I know we started doing those qualitative graphs. Can we do some of those? We really just sort of did a couple in class today. But they're really important. And I like the questions, too. Oh, yeah, I like these a lot. We might have done this one in class today. Y'all remember it? Was it exactly like this? Because I have lots of different variations. It looked like it, yeah, because I just have a big file with all my figures in it, and I just take it and I shift the graphs around, and then I make new questions. So your questions will look really, really similar to this, but It'll be different too. All right, so the one on the top is x versus t. And the ones in A, B, C, D, those are the velocity versus time graphs. The first thing I need to do is ask, what is the velocity positive or negative in this x versus t? And that's my question is then, what is the slope? Is it positive or negative? It's positive, right, positive. So that means I can get rid of A and D. I think this one might be a lot like the one we did. And then I ask myself, is the slope getting big or small? Is it increasing or decreasing the slope? It's decreasing. It starts big, it gets small. So that means that the answer has to be C. Let me give you another one. So what about this one? This is going to be an x versus t. Oh, what do I want to do? That's not a straight line, that's a curved line. Like that. Which one is that? Think about it for a few seconds. Is it negative or positive? And then is it increasing or decreasing in magnitude? It has to be either A or D. You're right in that because it has to be negative because it is a negative slope. But notice here that the slope up here is small and then the slope down here is big. Is that what D does? This is 0 right here. We can say this is like minus 10. That would mean this is like minus 2. So D starts big and then gets small. But A starts small right here at say minus 2, and then it goes to minus 10. So A is the right answer there. Hey, can y'all draw me the graph that looks like D? What does the x versus t graph look like for D? The x versus t graph for D is going to have a negative slope, and it's going to start out with a big slope and then get small. So sketch out that graph. That's right. What does that graph look like? Listen, on my exams, I often get free response. I haven't yet decided what I'm going to do for the exam. If you will get free response, I hope that you do because you benefit from it. Students tend to score higher when I give free response, but I don't know if I'm able to do it on the respondus. But anyway, sometimes I require students to draw these graphs to translate from one to the other. So I want you to translate option D into its position versus time space. You thought it through? Yeah? What you got? So it has to be a negative slope. To be negative slope, there are really only two options. It can look like this, or it can look like that. And so it has to look like that. Now let's see. So it has a big negative slope right there, and then it has a small negative slope right there. Need to be able to see those, how to translate from position versus time to velocity versus time. And if you're not getting it right now, that's fine. It will click with you. I guarantee that it will click. Just keep looking at it, practicing them. Every test I have has questions like this, so keep practicing that, and it will click for you. Okay, I'll take this away. This is a good exam. I like this exam. You want to see a preview of what we're going to do? Okay, you're going to have some kinematics questions. Many of them will be fairly simple, actually. I want you to be able to think about motion. I want you to know how to solve those kinematics equations and just be able to manipulate them algebraically. So with these problems like number 15, the first thing you want to do is just write down everything that you know. So it says a car is traveling at 20 meters per second. And what that 20 meters per second is our initial velocity. We haven't covered this in the class yet. Next week you'll be watching these, especially the blue group since y'all are out 2 days. So V naught, I always like to make a little thing over here. V naught is equal to 20 meters per second. And then it says it slows down at a rate of 10 meters per second squared. So the acceleration, that's A, is equal to 10 meters per second squared. Now here it says that it slows down. Now we'll get into this coming up, or y'all might have already gotten into it in the videos, where if velocity, or if it's speeding up, velocity and acceleration are in the same direction. Have y'all gotten to that yet? Y'all seen that in the notes? Okay. If you're slowing down, velocity and acceleration are in opposite directions. So if my velocity is in this direction and my acceleration is in that direction, that means I'm moving in this way, but I'm slowing down because I have this acceleration acting in that direction. You can think of the acceleration like a force. In fact, forces do cause acceleration. So you can think of this like I have this object moving in this direction, but it has like one of those parachutes that's acting to slow me down. Like I'm trying to run this way, but I got a parachute pulling me back, like a track athletes use to train. And then likewise, if V and A are in the same direction, then it's going to speed up. And so here this slowing down, I say all that because it's slowing down, that means the acceleration has to be opposite the velocity. And so that acceleration is going to be negative. I don't say that in the problem. I don't say the acceleration is negative. So you need to pick up on that with the language that I use. Because it's slowing down, it has a negative acceleration. That doesn't mean that slowing down is always negative. Because if the velocity was negative, that would mean that the acceleration would be positive. That would be slowing down. And we'll encounter that in other problems. And then I want to know how far does it travel. I want to know what is x. And I want to know the time in 2 seconds. So I say this one's a simpler one because it's really only a single step in solving it. We'll get into the equations. Actually, I think you got them in your video. And that was that there are 2 kinematics equations. V equals V naught plus AT. And then x equals V naught t plus 1/2 AT squared. Those are 2 kinematics equations. In fact, there are only a handful of equations that you're going to need for these first 3 or 4 chapters. And those are 2 of them. You need to know your trig functions, but I don't really think of that as memorizing an equation because you already know those, I think, in your Pythagorean theorem. Like, I think those are probably ingrained in your head. And then there's F equals ma. Those are really the only 3 equations that you need for the first 4 chapters. Now, chapter 4 is going to be a doozy, and there's a lot of vector math in that class, in that chapter, so it'll have its own complications, but memorizing formulae will not be the complication. Okay, so when I get all these unknowns, I'm looking for x, so I know I'm going to have to use this equation because that's the only one with x in it, and it turns out that I have everything that I need in order to solve that, so it's fairly straightforward. I just say v naught, which is 20, times t, which is 2, plus 1/2 a, which is minus 10, and a lot of students will trip up there because they'll put in positive 10, times 2 squared. And that's 40 minus 20. It's going to be 20 meters. Okay? Now, that took several minutes to work through, right? But when you get the hang, when you get the hang of it, you'll be able to move through it more quickly than that. All right, let's see what else we got. We'll just do a couple more. You have any particular questions as we get close to the end? Is helpful for y'all?
I have a question that's in there. It doesn't pertain to anything, but I just want to see.
All right.
I know I'm going to get to it.
All right. Shoot.
Like stuff with the floor.
Oh, torques. Yeah, that's not till chapter like 6 or 7. Can we hang on with that?
Yeah.
Okay. All right. Not today. All right. Okay, let's look at number 26. Number 26 is another one of these qualitative problems. And in this case, it gets to that idea of if my velocity and my acceleration are in the same direction, then it's speeding up. If my velocity and acceleration are in opposite directions, it's slowing down. And so I want to know what is the sign of the acceleration in this case. First of all, is this object speeding up or slowing down? What? It's slowing down. It starts with a really big slope, and then it ends with a small slope. So it's slowing. And so since it's slowing, I know that the velocity and acceleration are opposite. They're opposite one another. Velocity is in one direction, acceleration, just like the track star, right, with the parachute pulling them back, slowing them down. So the velocity and the acceleration are opposite. And so I know my acceleration is going to be opposite the sign of the velocity. And what is the sign of the velocity here? Positive or negative? What is it? It's negative. You're right. So here I know it's negative because my slope here is always negative. So I have an object that's slowing down and an object with negative velocity. Those two facts tell me that it has a positive acceleration. And we don't usually think of an object with positive acceleration slowing down, but in this case, that's what we have because it's moving in the negative direction. Don't think of positive, negative acceleration in terms of slowing down or speeding up or vice versa. Think of it in the terms of the direction. Is it in the same direction as the velocity or opposite the direction of velocity? Is that a question or just a? Okay. All right, let's look at number 27, and then we'll wrap up, unless you have more questions. This is another kinematics question. But it's more than a single step. So a car is initially at rest. That tells me that V naught is equal to 0. I'm going to write those equations over here, by the way. I have V equals V naught plus A times T, and then X is equal to V naught T plus 1/2 AT squared. Listen, on the test, you'll be allowed to have a blank sheet of scrap paper. I recommend that you just write those equations. As soon as the test starts, you write them down on there. On the test, you'll have your webcam. You'll show me sort of the paper that you have before you get started. So it'll need to be blank initially. But then as soon as you get it, you can write whatever you want on it. You can write a love note on that scrap paper for all I care. But I would write those equations just so you have them right in front of you. Okay? So it's initially at rest. It accelerates at a constant rate. In the first 10 seconds, so from t equals 0 to t equals 10, it travels 100 meters. And then I want to know how far does it travel after 20 seconds. I also know that V naught is equal to 0. So what I have to do here is I say X is equal to V naught T, which is just 0, plus 1/2 AT squared. And that means that 100 equals to 1/2 A times 10 squared. So A is equal to 1/2 of 100 is equal to 2 meters per second squared. So now I figured out that this object is accelerating at 2 meters per second squared. Now I can go to the second part of the problem, which is really just asking what is the distance now that it's traveled after not 10 seconds, but 20 seconds. And so it's going to be equal to 1/2 AT squared. The V naught term just goes away because V naught is equal to 0. 1/2 of 2 times t squared. T was 20 seconds squared. So that's going to be 400 meters. So the answer there is B. Notice that in the first 10 seconds, it travels 100 meters. And then after twice that amount of time, it travels 4 times that distance. So actually, this motion, where I have a constant acceleration of x versus t, looks like this. It's a quadratic function that as I double the time, I quadruple the distance because its x is proportional to t squared. Okay? All right, folks. That's all I have for now. Unless you all have questions, or if you have other questions, you can hang around if you need. I'm going to stop the recording.